Okay, so, chapter 4. Yes, ma'am.
If I remember correctly, we were supposed to finish up chapter 3
Oh,
in class.
really? All right, let's see. Thanks for letting me know. Chapter 3, so let me download that particular assignment.
He also said something about don't do question 20.
Don't do question 1.
Like something was wrong with it.
Oh, yeah, let's give it 20 because, this would have to do with gas laws and we haven't got the gases yet,
So
so,
just cross it out.
yeah. So where did we stop the last time for this assignment?
Question 12.
Well,
I was like, I know I didn't know.
okay, so question 12. Okay, so question 12 has to do with the whole concept of percent yield. Well, actual yield, theoretical yield, and percent yield. And those are topics that you should have encountered already in your previous chemistry experience. So in this case, and in all cases, whenever you're doing questions of this type, you have to make sure that the equation is balanced. So what I would tell students that they should do is to inspect the question, or I should say, inspect the equation to make sure it's balanced, right? Which it is in this case, right? And the question gives you the masses of the reactants, benzene and bromine. And the question is asking for the percent yield. They gave you the actual yield. And of course, you know that there's a difference between the actual yield and the theoretical yield. The actual yield, as the term suggests, is the amount of product that you get if you did the experiment and you isolate the product and you weigh it. That would be the actual yield, right? The theoretical yield is basically the amount that you would expect based on the amounts of reactants involved in the reaction, right? So that's what we have to calculate first in this particular case. So let me turn on my pen here. And put this up here. Okay. Okay, so what did I do? Okay, hold on. Okay, here's it. All right. So the first thing I would do is start off with the 30.0 grams of your benzene, C6H6, and I will convert that to moles. All right. So thank you. So 1 mole of C6H6, and down here I'll put the molar mass. So again, being the lazy SOB I am, I'm going to go to my molar mass calculator to calculate the molar mass of benzene. I think it's 78 point something, but let me. So C6H6. Okay, 78.11 grams per mole. So that number would go down here, 78.11 grams of C6H6. All right. So that's how we get to calculating the moles of benzene. Okay, so the next step is to find out, based on this, how much product you'd expect to get. And you could use any one of these two, it doesn't matter which one. I'm going to use the bromobenzene, especially because the question is asking for the percent yield based on the actual yield of bromobenzene. So based on the equation, it's a 1-to-1 mole ratio between these two, right? So I'm going to put 1 mole of C6H5Br and 1 mole of C6H6, right? And then I will work this out. So let me get my calculator here. So that will be 30.0 divided by 78.11 times 1. So, and please correct me if I'm wrong. But I got 0.384 moles of C6H5Br, all right? And then I do a similar calculation, but this time start off with the 65.0 grams of bromine. 1 mole of Br2 above, and down here the molar mass of bromine, which is, again, I'm going to go to my trusty Br2. So that's 159.81. So here I'm going to put 159.81 grams of bromine. All right, so that's how we get the moles of bromine, and then we look at the mole ratio between the bromine and the bromobenzene. Again, it's 1:1, so 1 mole of C6H5Br over 1 mole of bromine. And let's see what that gives. 65 divided by 159.81 times 1. So according to my calculation, this works out to be equal to 0.407 moles of C6H5Br. Okay, so now that we have done those calculations, what we do next is compare these two numbers to see which one is lower. And because this is lower, right, that means that this here is the limiting reactant. The benzene is the limiting reactant. And therefore, this is what we're going to use to calculate the theoretical yield. And the way we do that is that we take the 0.384 moles of C6H5Br and we convert that to grams. So we multiply by 1 mole of bromobenzene below and above the molar mass of bromobenzene. So again, I'm going to calculate the molar mass. C6H5Br. And let's see what this gives here. 157.41. So that goes up here. 157.01 grams of C6H5Br. And let's see what that gives. So 0.384 times 157.01. And according to my calculation, again, please inform me if I'm doing the wrong thing, but I got 60.36, so 60.3 grams of C6H5Br. And this, folks, would be the theoretical yield, right? So to answer the question is asking for the percent yield. So the percent yield is equal to the actual yield, which is 56.7 grams, divided by the theoretical yield, which is 60.3 grams, multiplied by 100%. So let's see here, 56.7 divided by 60.3 times 100. And according to my calculations, this works out to be equal to 94.0%. And that's how you do a typical percent yield type of question. All right. Okay, any questions about this particular problem? Any questions? As I said before, whenever you're doing these types of problems, I would check to make sure that the equation is balanced to begin with, right? Because if the equation is not balanced, then there exists a real possibility that the subsequent calculation will not be correct.
We're still on chapter 3, is that?
Awesome. Yeah, but somebody reminded me that we didn't finish chapter 3. Okay, any questions about this one? Any questions? Any questions? Okay, is it okay for me to clear this? All right, so let's clear that. Scroll down. Okay, let's see here. Now this one, similar type of problem. The only difference is they did not give an equation. They expect you to figure that equation out. So before you do anything as far as the math part is concerned, that's what you have to do. You have to figure out what the equation is, right? So the question is, what mass of water forms when solutions containing 3.27 grams of hydrochloric acid and 7 Oh, by the way, there's a paper going around, the tender sheet, where it are. Yeah. So this question, they gave you a certain amount of hydrochloric acid, a certain amount of calcium hydroxide, right? And the question is asking what mass of water forms when this happens, right? So, what you have to do is figure out what the equation is. So based on the information provided, we know that hydrochloric acid is one of the reactants, and calcium hydroxide is the other reactant. And we know that one of the products is water, right? So the question is there any other product, and what would that other product or products would be?
Calcium.
Calcium chloride? What's the formula for calcium chloride?
CaCl2.
CaCl2, very good, right? So that's the unbalanced equation, so now we have to,
Balance.
okay, so how would we go about balancing this equation?
There needs to be two hydrochloric acids.
Okay, two
two
HCl.
waters,
Anything else?
two water.
And to water, and that's it, right? So you have to do that first before you can do anything else, all right? Okay, so let's see what the question has given us. The question has given us the mass of hydrochloric acid and the mass of calcium hydroxide. So we're gonna do something similar to what we did in the previous problem, where we're gonna start off with the masses of each reactant and figure out, in this case, what mass of water you'd expect to get, right? So we're gonna start with the 3.27 grams of HCl. Again, you have to convert it to moles, so 1 mole of HCl, and down here, the molar mass of HCl, which would be HCl. Okay, so 36.46 would be the molar mass of HCl, so 36.46 grams of HCl. And then based on the balance equation, we can figure out how many moles, of water would be produced. And in order for us to do that, we have to look at the mole ratio between the water and the hydrochloric acid. That's a 2-to-2 or 1-to-1 mole ratio. So I'm gonna put 2 moles of H2O here, 2 moles of HCl here. And then we do the number crunching, so that's 3.27 divided by 36.46. And according to my calculations, rounded out to 3 sig figs, that gives us 0.0897 moles of water, all right? And then we do the same thing, starting with the 7.62 grams of the calcium hydroxide. So again, we convert to moles, 1 mole of calcium hydroxide over molar mass of calcium hydroxide. So let me go back to my calculator here. CaOH equals 62. And I got 74.09. So that would go down here. 74.09 grams of CaOH2. And okay, so then we look at the mole ratio between the calcium hydroxide and the water. And based on the balance equation here, for every 2 moles of water, there's 1 mole of calcium hydroxide. So the way we represent it here in this conversion factor is that we have 2 moles of H2O here and 1 mole of calcium hydroxide below. And then we do that calculation, 7.62 divided by 74.09 times 2. So according to my calculation, this works out to be 0.206 moles of H2O. So again, just like we did in the previous question, we compare these numbers here. And which one is lower? That one, right? So therefore, to answer the question is asking what mass of water. We have to convert that, which is 0.0897 moles of water, to grams. So the molar mass of water is 18.02 grams for every 1 mole. And we work that out. So that's 0.0897 times 18.02. And according to my calculations, this works out to be equal to 1.62 grams of H2O. And that's how that is done. All right. Any question about this one? Any questions? Questions? No questions? Okay, let me clear this, if that's okay. All right, so let me clear this. And let me see what's next. Oh, here's a B part. Okay. I guess I erased too quickly. I guess I'm gonna need you guys' help to do the B part. Oh, you know what? Hold on.
I
I
don't
should
think
be able
you
to
need
retrieve.
anything.
I'm sorry?
I don't think you need anything,
Um,
other than knowing the limiting factor.
okay, I'm able to retrieve it. Okay. I thought I lost it. All right. Thought I lost it forever. Let me do this here. How much in grams of the excess reactant remains unreacted? Okay, so basically, in order for us to answer that question, we have to identify which of the reactants will be the limiting reactant. And that, of course, would be the hydrochloric acid, right? And that's what we're going to start off with. We're going to start off with the 3.27 grams of the HCl. And what we're going to do is try to find out how much of the calcium hydroxide will react with this much acid, right? So we have to do the mole conversion first, like we did before. 1 mole of HCl down here would be 36.46 grams of HCl. And then what we have to do is look at the mole ratio between the HCl and the calcium hydroxide. That's a 2-to-1 ratio. So we're going to end up with 2 moles of HCl down here, 1 mole of calcium hydroxide above, right? And then the next conversion factor is that we convert the moles of calcium hydroxide to grams. So 1 mole of calcium hydroxide down here, and the mass of calcium hydroxide, which is 74.09, we calculated that earlier. Grams of calcium hydroxide, all right? So this is what we have to work out first, right? So let's see what that gives. 3.27 divided by 36.46 divided by 2 times 74.09. And according to my calculation, this works out to be 3.32 grams. Okay, so please note that this 3.32 grams of calcium hydroxide is the amount of calcium hydroxide that reacted, right? What the question is asking for is the amount of calcium hydroxide that remains, right? So how do we do that? Well, we take the original mass of the calcium hydroxide, which is 7.62, so let me just do that up here. So the mass of unreacted calcium hydroxide would be the 7.62, which is the amount that you started off with, minus the amount that reacted here, which is 3.32 grams. So let's see what I give. So 7.62 minus 3.32. So according to my calculations, I got 4.30 grams of unreacted calcium hydroxide remaining, right? And that's all that is done. All right, any questions about this one? Questions?
I'm just wondering, because I did this one at home, I got 4.31. Would that be?
I'll have to look at your calculation.
Okay.
You probably rounded some.
Yeah, maybe there's like a rounding. Sometimes when you round off too soon. Or round off incorrectly, then you get a slightly different answer. I'll have to see the numbers that you're working with. Okay, any other questions about this one? Any other questions? All righty, let me clear this here. Is there a C part? Oh, okay. Okay, all right, so number 14, and apparently subsequent questions after that deals with concentrations. Now, just to rehash or review, when we're talking about concentrations of anything in a solution, generally speaking, we're talking about the amount of that particular solute present in a given amount of solvent, all right? Now, there are different ways of expressing concentration. The most common one is molarity. So let's just write down the definition of molarity right here. Molarity, by definition, is the moles of solute divided by liters of solution, right? It's the moles of solute divided by the liters of solution, okay? So basically, in practice, and this is done in labs all over, including here, and even including, the most advanced research facilities. In order for you to make a solution of a particular molarity, you have to find out first the moles. How do you do that? Well, of course, you need a molar mass, and you need basically to find moles and then find the equivalent mass of that. And then you basically put it in a piece of glassware known as a volumetric flask, which I don't think those of you enrolled in my lab are introduced to this quite yet, but it looks something like this. Now, please forgive my poor artistic skills. I've never been blessed with the ability to draw. But basically, it is a flask which has a kind of round bottom with a flat end here, right? And they come in different sizes, right? The smallest one I've seen is, I think, a 10 ml volumetric flask, and you can get them up to the largest one, which I think I've seen is 2 liters, all right? And basically, they are very accurately made, and they come with a mark etched on the stem here, which represents a specific volume, right? So in the case of, let's say, 100 ml volumetric flask, if you add liquid up to where the meniscus gets up to this point, then you know that you have accurately measured a 100 ml volume of that particular liquid, right? So typically what is done is that you add your solute to your flask, and then you add your solvent, let's say water to it, and then you add water to about here, right? And then you stopper it, shake it up to make sure it dissolves, and then you continue to add water dropwise until the meniscus gets up to that mark, and then you shake it up again just to make sure that the solution is homogeneous, and then that's it. That's how you make up your solution. And for those of you enrolled in my lab, you were in my lab yesterday, right? Right. So they did the experiment already. Guys in this lab here, you haven't done the experiment yet, but you're going to get the opportunity to learn how to make up solutions of specific molarities and dilution and so on. All right. So with that said, let's look at question number 14, which says, how many grams of potassium carbonate are needed to make 200 mils of a 2.5 M solution, right? So this is the equation that we're going to use. The first thing we need to do is find the moles of the solute. So you get the moles of the solute by multiplying the volume of the solution by the molarity, right? But the volume has to be expressed in liters. Here they gave us the volume in milliliters, right? So what I would do first is convert that to liters. So I'll multiply by 1 liter over 1,000 mils, all right? So that this will go with that. And then the next step is that I multiply by the molarity. Now remember, well, I don't think I've told you this, so let me say that now. The unit of molarity would be, based on this here, moles per liter, right? But it is also represented, this collection of units is also represented by uppercase M, right? So whenever you see uppercase M in reference to the concentration of a solution, you should remember it stands for moles per liter, right? So for that reason, this 2.5 M here, I'm going to represent it as 2.5 moles over 1 liter, all right? So the liter units will cancel out. But remember now, the question is asking how many grams, right? Which means that I would multiply this by the molar mass of potassium carbonate. So up here, I'm going to need the molar mass of potassium carbonate. So K2CO3, 138.1.21. So that goes here, 138.21 grams. All right, so that's how we set it up. So the next step is to, of course, do the number crunching. So that's 200 divided by 1,000 times 2.5 times 138.1. And according to my calculation, this works out to be equal to 69 grams, because you have to round off the 2 sig figs because of this. So 69 grams of the solid potassium carbonate you're going to weigh in order to make this particular solution. Okay, any questions about this one? Any questions? Any questions? Okay, so let me clear this. All right, now let me see if you can tell me how you'd approach question number 50. It says, how many liters of a 4M solution can be made using 100 grams of lithium bromide. So let me hear your suggestions as to how you tackle this problem. And you guys out there in Zoom, feel free to chip in. You are part of this class too, all right? So let's hear it. The question is asking for the volume because it says how many liters, right? The question gives you the molarity and the mass of the lithium bromide. All right, so any ideas? And also, let me just remind you of the formula. Molarity is equal to moles of solute divided by liters of solution. Okay, so let me hear your ideas.
You gotta turn grams into moles.
Okay, so you turn the 100 grams of lithium bromide. What's the formula for lithium bromide?
LIBR.
LIBR. Okay, very good. So how do we convert that to moles?
You're going to do on the bottom,
Mhm.
86.84 grams.
I'm sorry?
86.84 grams.
Okay.
of
I'm gonna take your word for it. If I get it wrong,
ice
it's
cream.
our fault. All right, but I think that sounds right.
86.84,
0.84, okay.
Yeah.
And what goes above here?
1 mole. of
1 mole
LIBR.
of lithium bromide. Okay, very good. All right, so that will give you the moles, right? So the gram units will cancel out. What's the next step?
Then you have to use your molarity.
Okay, so how would that come into play? Because remember, molarity is moles per liter, oops, right? The units is moles per liter. So how would you set up the next conversion factor here? What would go up top here and what would go below here? I'm sorry?
1 liter above.
1 liter above, and what goes down here? 4 moles of lithium bromide below. All right? Okay, very good. And that's it. That's the setup. So 100 divided by 86.84 and then divided by 4. So according to my calculation, this works out to be 0.288. Oh, wait a minute. No, I have to round off to 1 sig fig. So that would be 0.3 liters. And that's how that is done. All right, any question about this one? Questions? Okay, number 16. In this case, it's asking for the concentration. They gave you the volume, they gave you the mass. So how would you go about solving this one? Basically, the question is asking for the molarity, right? And by definition, molarity is moles of solute divided by liters of solution. All right, so let me hear what you have to say about this one.
Well, milliliters have to go to liters.
Okay, so that goes below, right? 450 milliliters. So how do you convert from milliliters to liters?
1 liter of
And
1,000.
1,000 mils below, very good, all right.
Sorry, I have
Yes, sir.
one question about the last one.
Oh,
You
sorry,
said
yeah.
1 sig fig, but there was a decimal place after the,
Right, but because of this 4 right here,
okay.
right?
Uh,
So it's 1 sig fig, right? Even though you're right, there are 3 sig figs here, but you have 1 sig fig here for the moles. Okay, going back to question 16. So what would you put up top here as the numerator?
You're gonna do the grams
200 grams,
of FeCl2,
right?
and then you're going to do, your molar mass
Okay,
on the
so,
bottom.
okay, what's the molar mass?
It is 126.75 grams of FeCl2.
All right, again, I'll take your word for it. And what goes up here?
1 mole.
1 mole of FeCl2, okay. And that's it, that's the setup. So let's see what this gives, 200 divided by 126 point, what's that, 75?
75.
And then I'm gonna divide that by 450 divided by 1,000. And according to my calc, now this have to round off to 3 sig figs. So the answer here is 3.51 M. And that's how that is done. All right. Okay, any questions about that one? Yes,
when-
ma'am.
When we're taking our exam, are you okay if we use M or
It doesn't matter which one, they're both correct, right, if it's M or moles per liter,
I find myself doing both.
right. You might find it more convenient in terms of, you know, showing the setup and the units cancellation. If you use moles per liter, right, because that you can, you know, see clearly what units being cancelled out and so on. But both are just as correct. Okay, any other question about this? Any other question? All right, let me just check out something here because I think it's okay for me to leave some of these for you to do on your own. Let me just check on this here. So that's 17, 18. Okay, tell you what, so I'm gonna leave 17 and 18 for you guys to do on your own. If you have any problems while doing it, please feel free to contact me about that. All right, so let's look at number 19. Now, number 19 is one of those, what I call solution stoichiometry type problems. It says for the following questions on this worksheet, consider the following equation, which is given. And the question, the A part is asking, what type of chemical reaction is taking place? And the answer is what?
Acid base.
Acid-base neutralization, or you could also say double displacement reaction. Both are just as correct. So the B part is asking, how many liters of 0.100 m hydrochloric acid would be required, excuse me, to react completely with 5.00 grams of calcium hydroxide? So the way I go about solving this one is that I would start off with the 5.00 grams of the calcium hydroxide, and I will convert that to moles. So 1 mole of calcium hydroxide above, and the molar mass, I think we calculated this earlier, was it 74.09 grams? That sounds like it. Calcium hydroxide, okay. And then, so this unit will cancel out with that. Then what I would do is look at the mole ratio between the calcium hydroxide and the hydrochloric acid. That's a 2-to-1 mole ratio. So I'm going to put 2 moles of HCl above and 1 mole of calcium hydroxide below, right? So that this goes with that. And then to get the volume, what I would do is make sure you sign the sheet. Where is it? Where's the sign sheet? Here's the sign sheet. So to get the volume, this is where the molarity comes in, right? So the way I would represent that here is that I would put below 0.100 mole of HCl. The numerator above would be 1 liter of HCl. And that's it. So this unit will cancel with that unit. So all we have to do is 5 divided by 74.09 times 2, and then divide by 0.1. And according to my calculation, this works out to be equal to 1.35. Is that correct in terms of 650? Yes, okay. So 1.35 liters of HCl. All right. And that's all, okay. That's all that is done. All right. Any questions about this one? Any questions? No question? Okay. In the case of okay, let me clear this here. I'll scroll down. In the case of C, this question says, if I combine 15 grams of calcium hydroxide with 75.0 mils of 0.50 mHCl, what is the limiting reactant? So this is a limiting reactant type of problem. And we did a couple of those types earlier, but this one is a bit different because this one has a component where you're dealing with a solution of a specific molarity. But the approach is pretty much the same. So let me just show you how this will be done. What I would do is start off with the 15.0 grams of the calcium hydroxide. And I will convert that to moles like we did before. So 1 mole of calcium hydroxide over 74.09 grams of the same. And then the mole ratio this time would be between the calcium hydroxide and the product. And you could choose any one of these 2 products. I'm going to use the calcium chloride as the product that we're going to use. So basically that's a 1-to-1 mole ratio. So basically I'm going to put here 1 mole of calcium chloride above calcium chloride and 1 mole of calcium hydroxide below. All right, so let's see what that gives. 15 divided by 74.09. And according to my calculation, this works out to be 0.202 moles of calcium chloride. And then I do the same thing with the hydrochloric acid, excepting that I'm starting off with 75.0 mils of HCl. Now, what I would do first is convert that to liters. So 1 liter of HCl above, 1000 mils below of HCl. So that goes with that in terms of the units. And then I would convert the liters of HCl to moles using this value right here. So I'm going to put above as a numerator 0.500 moles of HCl and below as a denominator 1 liter of HCl. All right, so that this will go with that. And then the next step would be the mole ratio between the calcium chloride and the HCl. And if you look at the equation, you'll see that it's a 2-to-1 mole ratio, where above I'm going to put 1 mole of calcium chloride, and below I'm going to put 2 moles of HCl. Right? And then let's see what I get. So 75 divided by 1000 times 0.5 divided by 2. And according to my calculation, this works out to be 0.0188 moles, right, of calcium chloride. So just like before, the previous problems of this time before, we compare these two numbers to see which one is lower. This one is lower, of course. So therefore, that means that HCl is the limiting reactant. And that's how you do that. All right. So that's basically how we answer the C part. Okay. Any questions about this? Any questions about this one? Okay, the D part is asking how many grams of calcium chloride do we form? But that's easy. All we have to do is take the lower number here, which is 0.0188 moles of calcium chloride. And we have to convert that to grams. So that means we need the molar mass. So we're going to put 1 mole of calcium chloride down here. And above, we're going to put the molar mass of calcium chloride. So CaCl2. And that's 110.98. So I'm going to put 110.98 grams of calcium chloride above. And then we have to work this out. And according to my calculations, this works out to be 2.09, I'm sorry, 2.09 grams of calcium chloride. So that's what you'd expect to be the amount of calcium chloride to be formed. All right. Any questions about this one? Any questions? Okay, let me go ahead and clear this. And scroll down. Oh, here's an E part. How many grams of excess reactant will be left over after the reaction is complete? This is kind of similar to one that we did before. I don't remember which one it was, but basically what we have to do is start off with the limiting reactant. Get back. Okay. So to get how many grams of the excess reactant remaining, we have to start off with the limiting reactant, which is the HCl. So let me write it up here before I erase that part. So 75.0 mils of the HCl, convert to liters, 1 liter of HCl over 1000 mils of HCl. And then the molarity, finding moles using the molarity, so 0.500 moles of HCl over 1 liter of HCl. And then we look at the mole ratio between the HCl and the calcium hydroxide, which is a 2-to-1 mole ratio. So you're gonna have 2 moles of calcium hydroxide here. 1 mole of HCl above, below. All right, so to avoid confusion. Let me erase all this down here. Oops. Like that. So this should be 1 mole of HCl here, okay. Let me just see this bottom part here.
I think the 2 moles would be HCl.
I'm sorry, you're right. This should be 1 here, my bad. This should be 1 here. And this should be 2 here, so let me change it up. So this would be 1 mole of calcium hydroxide. And this will be 2 moles of HCl, all right? And then what we have to do next is to find the mass of calcium hydroxide. So we multiply this by the molar mass of calcium hydroxide. The molar mass goes up here. What's the molar mass of calcium? Did you?
74.09.
Keep forgetting, right? 74.09 grams of calcium hydroxide. Okay, very good. So this is what we have to work out. So let's do that. 75 divided by 1000 times 0.5 divided by 2 times 74.09. And according to my calculation, this works out to be equal to 1.3, 1.39, 36 grams of calcium hydroxide. And this is the amount of calcium hydroxide that reacted. The question is asking how much of it could be left over. So what was the original mass of the calcium hydroxide?
15.
15.0?
0.00.
So mass,
Oh,
Of
it's
cal-
15.0, sorry.
I'm sorry,
I added an extra 0, there's
Oh.
only 1.
so mass of calcium hydroxide remaining would be 15.0 grams minus 1.39 grams. So let's see what I get. 15.0 minus 1.39. So according to my calculation, this works out to be 13.6 grams. And that's how you do that. Yes, ma'am.
So I did it differently,
Okay, let's hear what you have.
but I got the
And-
same
and-
answer.
Before you say that, this oftentimes happens, right? Sometimes somebody will run a problem or work a problem using a different way. The result should still be the same if the way they did it is just as legitimate, but let's hear what you have to say.
So because in C, we figured out the limiting reactant created the moles of CaCl2.
Okay.
So I decided to take those moles and compare the mole ratio of
Okay.
PaCl2 to CaOH2.
Okay,
And then multiply by the molar mass. So it
and that
was
gives you the 30.6,
1.39.
1.39, okay,
And then I subtracted,
that's just as
because we
reasonable.
already figured out the product.
Right, exactly, right, that's just as reasonable, actually, yeah, so, yeah, that happens time after time in chemistry. Where, different people, sometimes, unfortunately, not in this case, but sometimes unfortunately, some people take a longer route to get to the same answer. Which I wouldn't take off points for, because as long as it's legitimate, it's fine by me. But basically, what you suggested is pretty much would take about the same amount of time as what we did, but it's just as legitimate, so you get full credit for that as well. All right, any other questions about this one? Any other questions? Okay, so as I said before, we skip number 20. Let me clear this first. So let's see, 21. Okay, I'm gonna leave 21 for you to do, because 21 is similar to what we just did, right? So again, if you have any problems while doing that, let me know. And let me see here. Number 22 is very similar too, actually. So yes, do that one on your own as well. Oh, and that's it? Yeah, you realize it was Okay, so that's basically it for chapter 3. Let me just check something here. Okay, so for chapter 4. I don't know if you guys had a chance to watch the videos for chapter 4. So what I'm going to do is I'm going to start with the earlier part of it. And again, some of this should be a bit of a review from what you did in introductory chemistry or high school chemistry. How am I going to do this? All right, tell you what, let me go to files. So in chapter 4, we're dealing with aqueous solutions, chemical reactions that occurs in aqueous solutions. And one of the first things that we need to remind ourselves of is the nature of ions. As you all know, ions are basically species that carry charges, and the charges can be positive or negative. And okay, so this is just summarizing the nature of the electrical properties of charges. And as we all know, like charges repel each other and unlike charges attract each other. So this is just basically a model showing you how these charges behave. If you have two charges suspended from a fixed platform, right? If they're neutral, there'll be no electrical attraction between them. But if they are opposite in charges, then they'll attract each other. And if they are the same charges, then they will repel each other, all right? And it's kind of similar to how bar magnets behave. I'm quite sure you have played with magnets. And if you have two bar magnets and you bring two like poles in close proximity to each other, they will repel each other. But if you bring a north pole in contact or in close proximity to a south pole, then there will be an automatic attraction between those ends, right? Now, as far as ions are concerned, one property of compounds that contain ions is their ability to conduct electricity under certain circumstances. Now, in a solid state, that won't happen. If you have a solid block of an ionic compound, let's say sodium chloride, and you stick 2 electrodes in them and connect it to an external circuit, there will be no electric current flow, right? What is required, in fact, for the flow of an electric current is the fact that the charges are mobile, right? In the case of an ionic compound, the charges are not mobile, they're fixed, right? So therefore, an electric current will not pass through. Now, if you could get the charges to be mobile, to be free-flowing, then basically, in that state, the compound will be able to conduct electricity. And there are 2 ways you can achieve this. One is if you heat the ionic compound to its melting point, which would be a very high temperature, right? If you heat it to its melting point, then the ions will be free to move around. And therefore, if you stick electrodes in them, an electric current will flow through the external circuit. Another way you can get the ions being free-flowing is if you dissolve the ionic compound in water, right? The compound will break up, you're going to have the positive and negative ions floating around. When you stick 2 electrodes in it, connect it to an external circuit, then you're going to have a current flowing through the system, right? So basically, the only 2 ways that you can have an ionic compound conducting electricity is if the ionic compound is in a liquid state. The term that is used in this case, we say it's molten. Molten basically means that in order for you to convert a solid to a liquid, you need to heat it to a very high temperature. And that is true for all ionic compounds. The temperature would have to be in the hundreds of degrees Celsius in order for it to melt, right? Or if you dissolve the ionic compound in water, then the compound in the solution will be able to conduct electricity, because what is required for an electric current to flow through the solution is the mobile ions present, right? So that's the setup being shown here. I think this is representing what happens in either molten or aqueous states. You have the external circuit connected to two electrodes, right? This is the electricity source, and this shows you the flow of electrons, right? And as you can see here, because of the flow of electrons from here and coming down here, this electrode will be positively charged, this electrode will be negatively charged. So what's going to happen is that the negative ions will be attracted to the positive electrodes, and the positive ions will be attracted to the negative electrons, all right? So that's basically how the electric current will flow through the solution and also through the external circuit. In fact, the particles responsible for the electric current to flow through the external circuits, those would be the electrons, as you can see here and here. While the particles responsible for the electric current flowing through the solution or the molten state of the ionic compound would be the ions, all right? Okay, so let's see here. Okay, so this electrode, I should have mentioned it, is called the anode, right? And this electrode is called the cathode, right? And that's the reason why the negative ions are called anions, because they're attracted to the anode, right? While the positive ions are attracted to the cathode, all right? Now, basically, when it comes to aqueous solutions, there are three main categories with respect to their ability to conduct electricity. They can be what you call non-electrolyte solutions, and then you have electrolyte solutions that are weak, and then you have strong electrolyte solutions, right? In the case of non-electrolyte solutions, basically they contain no ions, right? And because they contain no ions, they are not able to conduct electricity. So the example that is shown here in this picture is a solution of methanol. Methanol, when added to water, does not dissociate to form ions, right? So basically you're going to see, well, if you could see the molecules, you'll only see intact methanol molecules present, no ions present, and therefore if you try to run a current through it, which is basically what is being done here, we have a lamp which is a part of the external circuit. As you can see, it's not lighting up, which indicates that there's no current passing through the solution, right? So this is called a non-electrolytic solution. In the case of solutions which contain strong electrolytes, basically what that means is that the compound or the solute that is dissolved in water will immediately break up or dissociate to form ions, right? So again, if you could see the particles in the solution, in addition to the water molecules, you're going to see the separate ions. You will not see the intact solute particles present or the ionic compound present as an intact entity, right? You're going to see free floating ions floating around in the solution. And for that reason, that solution will be a very good conductor of electricity. And that is indicated by the fact that the light here is shining very brightly, indicating that this solution here is a solution of a strong electrolyte. On the other hand, you have this solution here where the light does not light as brightly, and that's because this is a solution of a weak electrolyte. In fact, the solute in this particular case is acetic acid. Acetic acid is a very weak electrolyte in that it does not break up completely to form ions, right? Basically what that means is that only a small fraction of the acetic acid molecules will be converted to ions, and therefore, as a result, because the concentrations of the ions are low, that means that the solution itself will not be as good a conductor of electricity as in the case of sodium chloride. So that is, of course, as I said before, indicated by the fact that this light here does not light up as brightly as in the case of a strong electrolyte, all right? So that's the difference between strong electrolytes and weak electrolytes. Now, when it comes to strong electrolytic solutions, we can actually determine the concentration of the different ions based on how the compound dissociates. Now, before we get into looking into that, I want to introduce to you this representation, which you may not have been introduced to in your previous chemistry experience. Whenever you see the formula placed within square brackets or parentheses, basically what that means is molar concentration of what's within the parentheses, all right? So for example, if I gave you this, something like, if I gave you something like this, right? What this means is the molar concentration of HCl is equal to 0.50 M, right? So basically, that's how you interpret this symbolism here, all right? Now, let's look at what happens when we start off with a solution of sodium chloride where the molarity is 0.010 M, right? Now, sodium chloride is an example of a strong electrolyte because when sodium chloride is added to water, all of it dissociates to form sodium and chloride ions according to this equation, right? So basically, if you look at the stoichiometry of this equation, it's a 1:1:1 mole ratio between the sodium, which you start off with, the sodium chloride that you start off with, the sodium ions and the chloride ions, right? So based on the stoichiometry of this equation, we can come to the conclusion that in a solution where you start off with 0.010 M of the intact sodium chloride, the resulting solution would have a molarity of 0.010 M with respect to the sodium ions and 0.010 M with respect to the chloride ions. And you could also say that the total molarity of the ions in this solution would be equal to the sum of these two, the 0.010 and the 0.010, which would be equal to 0.020 M, right? So sometimes you need to know what the total concentration of the ions are, and that's basically how you determine that. And I think I have another example lined up here. Okay, I thought I had another example here. This is the example I was thinking of. Let's say you had a solution of sodium sulfate, where the molarity is equal to 0.010 again, all right? Now, in the case of sodium sulfate, you have to pay attention to the stoichiometry to determine the total concentration of ions, right? So in the case of sodium sulfate, when it dissociates, when you add it to water, it dissociates to form Na plus aqueous, but this will be two of them because of this two here, plus SO4 2 minus aqueous, all right? So in this case here, for every 1 mole of sodium sulfate that dissolves, 2 moles of sodium ions will be produced, and 1 mole of sulfate ions will be produced. So therefore, based on this dissociation, we can say that the concentration of Na plus would be 2 times 0.010 M, which would be 0.020 M, and the concentration of the sulfate ion would be, because of the 1:1 ratio between these two, 0.010 M. And we can say, therefore, in this solution, the total concentration of the ions would be the 0.02 plus the 0.010, which would be 0.030 M, right? And that's basically how we can determine the total ion concentration based on the formula of the ionic compound to begin with, right? Now, please note that this type of calculation can only be done if we know that the compound will undergo complete dissociation, right? In other words, it's a strong electrolyte, right? As you're going to see, and as we have seen before, not all compounds that add to water, or when you add it to water, will undergo complete dissociation. Some will undergo partial dissociation, and that would be that would result in a weak electrolytic solution. And then you have others that will not dissociate at all, and that will give rise to a non-electrolytic solution. All right, what time is it? Okay, here's the thing. Okay, let me clear this.
Are we gonna be turning in chapter 3?
Yeah, I'm going to set up a jump box so that short.
Okay.
Okay, I think this is going to be probably the last topic we're going to talk about here. So, if you understand what we talked about in terms of weak and strong electrolytes, then we can apply the same concept to acids and bases, right? So you can have weak acids and strong acids. You can have weak bases and strong bases, right? So basically, a weak acid is one that undergoes partial dissociation, or incomplete dissociation when added to water, right? So we met one example of a weak acid before, and that was acetic acid. As we said before, only a small fraction of the acetic acid molecules will be converted to ions, right? And then you have strong acids which undergo complete dissociation, right? So again, when it comes to their ability to conduct electricity, what you're going to find is that strong acids will conduct electricity very well when dissolved in water, while weak acids will not be as good a conductor of electricity in water, right? Now, in terms of representing the type of dissociation that takes place in the case of strong acids versus weak acids, in the case of weak acids, we use a double arrow, meaning arrows pointing in opposite directions in the balance equation to represent the fact that the dissociation is partial or weak. So in the case of acetic acid, this is how we represent what happened, right? Because what actually happens in the case of an acid that is weak is that the forward reaction will take place, but at the same time, the reverse reaction will take place. So you have this back and forth taking place, right? Until you get to what is called a state of dynamic equilibrium. And for those of you who have to do general chemistry too, we're going to delve into that in more detail. If you happen to be in my class or any other class, you're going to delve into that particular topic, right? Equilibrium systems, right? And how different factors affect the position of equilibrium and so on, right? So this is an example of an equilibrium system, and this is true for all weak acids. All of them dissociate partially because of that back and forth where the products become the reactants and vice versa, all right? And this is just a modelistic model representation of the same process, right? Now, this begs the question, how can we tell the difference between strong acids and weak acids? Well, this is one of the few times where I would expect you to memorize some stuff. If you have had me before, and I think I mentioned this maybe earlier with you guys, I'm not a big fan of memorization when it comes to chemistry, right? You know, I believe that the best way to learn chemistry is engage in problem-solving exercises, right? I know some colleagues of mine, they expect students, for example, to learn all the ions in the chart that I provided for you. I'm not into that, right? But there are a few things that you need to memorize, and this is one of them for me, right? Before I get into that, so typically, strong acids are represented where the hydrogens are placed first in the formula, and then weak acids are ones where the hydrogens that will dissociate will be placed at the end of the formula. But this is not universal, right? But you know, in some cases, that's what you see. So this is where you have to memorize the strong acids here. These 6 acids you need to memorize as strong acids, right? Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric, right? Pretty much all acids that you're going to meet, which don't fall in this list, that you're going to meet later on will be weak acids, right? And if there are any other exceptions, I'll let you know, right? But you need to know these, or you need to memorize these 6 acids as strong acids. And let me just make a special mention of sulfuric acid, because you'll notice that in the case of sulfuric acid, you have 2 hydrogens here, right? It turns out that in the case of sulfuric acid, let me put it down here. In the case of sulfuric acid, the first dissociation, where 1 hydrogen ion is lost, is a strong dissociation. So that would be H plus HSO4 minus, right? This dissociation is strong. In other words, all the sulfuric acid molecules here will be converted to ions, right? But the second dissociation, where this loses a hydrogen ion, is weak. So that's why I'm using the double arrow representation here to get H plus SO4 2 minus, right? So the first dissociation is strong in the case of sulfuric acid, but the second dissociation is weak. And that's a very important distinction that you need to keep in mind, all right? Because that can affect some other things that we're going to do in terms of, for example, determining the net ionic equation of a reaction, all right? So that's basically the list of 6 acids that are strong that you need to memorize, all right? Okay. Okay, so that's it as far as recognizing which acids are strong and which are weak. So the next slide, I think, has to do with bases, right? And the same concept applies. Let me just get rid of this here. As far as bases are concerned, you have strong bases and weak bases. And basically, bases are ionic hydroxides, The strong bases are ionic hydroxide, which when added to water undergoes complete dissociation, and therefore they're good conductors of electricity. Weak bases are typically molecular compounds, which produces hydroxide ions, but basically the concentration of hydroxide ions are not great, and that's because there's a back and forth again, as in the case of weak acids. So one example of a weak base is ammonia. Oops, I'm sorry. And in the case of ammonia, let me show you how that works. When you add ammonia to water, this is what happens. NH3 plus H2O give you NH4 plus and H4 plus OH minus, right? And as you can see again, the double arrow indicates the back and forth, right? So ammonia is an example of a weak base, and there are other weak bases. Most of them are organic amines, all right? So that's basically a weak base. And again, because of the back and forth, the concentration of OH minus is very low. And the concentration of this is also very low, and therefore, weak bases are not as good a conductor of electricity as in the case of strong bases, all right? And as far as identifying which bases are weak and which are strong, that's even an easier list to remember, because here's a list right here. These are the list of strong bases, right? You don't even need to memorize them, excepting that you need to recognize that they're from groups 1A and 2A, the hydroxide of those ions, right? So therefore, those are the strong bases. Pretty much all of the bases that you're going to encounter in this course will be weak bases. All right, I think I'm going to stop here. Let me just check something. Okay, I'm going to stop here for today. All right, so as she was asking, what I'm going to do now is set up a Dropbox for assignment number 3. Okay, so I'm going to go here. Publish this. And let me see here. Okay, so today is the 10th. So this is the 10th. Okay, I'm going to give you until the 14th to submit assignment number 3. So let me make sure that this is set up correctly. So this will be available from now until the 14th. I'm going to save it just to make sure. And let me just check here just to make sure everything is in place. Okay, so everything's in place. Okay, so that's that as far as when your assignment frees due. So remember, the test is in the testing center. If you haven't done the test already, make sure that I don't remember how many pages, but I think I posted an announcement about the number of pages, right? So when you go to do the test, make sure that it's, the number of pages is as I stated, including the cover page. I should have mentioned that, right? So including the cover page and the other pages, there should be 7 pages, right? If you get anything less, let them know, right? And if they give you any trouble, then contact me, all right?
And then did they give us the tables or could we bring?
They need to provide the tables as well, right?
One more thing, so I've never used the testing center. Do you go there, you schedule it?
Well, you have to make an appointment online.
Okay.
Right, so go to the testing center website. You go to the college website, and I think you can access the testing center website there. Make an appointment, and please make sure that you meet that appointment, because I got an email from the testing center. They were saying that apparently in the past some students have been scheduling appointments and not making it. So make sure that you go to the appointment. If you can't make it, let them know, because apparently the amount of slots is limited, and they want to make sure that people have the opportunity to do the test. Another thing I need to mention too. So number of pages. Oh, and I also made sure that I put what you should see on the cover page in terms of the title and so on. The main thing you should look for is spring 2026, right? And the reason why I mentioned that because last semester there was a whole other situation where they gave students tests from previous semesters, right? So look for spring 2026, right? If it doesn't see that, if you don't see that, then let them know that's what you should get. And again, if you have any issues with them, then contact me, just send me an email or leave a voicemail message, and then that means I have to call them and try to work that out, all right? And I think that's probably all I have to say concerning that. All right? Unless you're any, oh, you have a question?
Are we continuing chapter 4 video?
Yes, make sure you watch the chapter 4 videos. I think I published them. Let me make sure. Okay, so basically what I've done today is this and this. So if you watch those videos, it's basically repeating what I just said today. So watch the rest of it. And then come prepared to, oh, you guys have assignment for already, right?
Yeah.
Yes.
If that's good, because what you guys can do on your own while you're watching the videos is try to solve it. And then we can get together and discuss, those problems in class, all right? That makes my life a lot easier.
Are there like any past testing examples that you study?
Good question. Let me see if I published any of those. So let's see here. Test content is. Let me try this one right here. Okay, I have test numbers 1 through 3 for spring 17. So let me go back here. What's going on? Okay, I missed out. Ah. Okay, so that's one. Okay, so I'm going to publish this right here. Okay, so you have access to that. And that would help you in terms of review.
Okay.
Yeah.
And then when you make an appointment at the testing center, are you able to select like the class and the professor?
I think the way I've never done it, but from what I've been told, you can, I think when you come to that part of it, I think they have time slots.
Okay,
And then you select the time slot, and you can do it at any of the 3 campuses.
Okay.
Whichever is convenient to you.
I appreciate it, thank
Yeah,
you.
no problem. Okay, and you guys out there in Zoom, unless you have any questions in the next minute, I'm signing off. Any questions? No questions? Okay, I'm signing off right now. All right, so I'll see you next class.